Okay. So now we discuss on the slope stability analysis. Okay. For this section, okay, I will discuss on the infinite slope. Okay, civil engineer often are expected to make calculation to check the safety of natural slope, slope of excavation and compactor embankment. This check involves determining the shear stress developed along the most likely rupture surface and comparing it with the shear strength of the soil. Okay. So the process is called as slope stability analysis. The most likely rupture surface is the critical surface that has the minimum factor of safety. Okay. So means that in one analysis, okay, there will there will be a lot of uh, a lot of rupture surface potential to be occur. Okay, so then we need to identify which one is the most critical surface. Okay, by having a lot of uh, analysis that been carried out. Okay, okay. Okay, we go this in very deep, okay, to understand on how the derivation of the safety equation. Okay. So, sorry. So from the previous discussion, okay, we know that there is a driving force, okay, and also a resisting force, okay. By having what we call as a simple analogy of a block, soil block on the failure plane, okay. So then we can understand, okay, that the driving force, okay, the equation is W sine theta, okay, while for the resisting force, okay, basically M is mu, which is mu W cos theta, okay. So mu actually is the F over N, or the tangent phi, which is the uh, tangent of the uh, internal friction angle. Okay. So the factor safety or the transitional slip is defined as FR, okay, over FD. Okay. So the FR is the resistant force, mu W cos theta, okay, over W sine theta. Okay. So from the um, mu, okay, actually it is a ratio between F and N, or which is from the tangent phi. Okay. So then for okay, cos over sin, basically, okay, okay, this is new. Okay, so new become tangent phi. Okay, so W you can eliminate. So cos over sin actually is a inverse tangent. So if inverse tangent, it become tangent theta. Okay. Clearly, when the dp angle theta is smaller than the angle of friction, the resisting force Fr is greater than the driving force Fd. Then the factor 1 and the factor safety is greater than 1, and vice versa. Okay, when factor safety is 1, greater than 1 is safe. When factor safety is equal to 1, so it is considered as a critical or onset of failure. So when the factor safety is less than 1, it is failed. Okay. So as I mentioned before, okay, in order to make sure that your slope is stable, okay, you need to make sure that the angle of the slope is less than the friction angle of the soil. Okay. So let's say for a compacted type of material, okay, the phi angle is around 33. Okay, so that is why when we propose for the construction of the embankment, okay, we may use or we may construct for the angle of the slope by using the 2 to 1 degree or 2 to 1 angle, which is almost 27 degree. If you use 2 to 1 ratio for the slope gradient. Okay? So if 27, so it means that it is less than the friction angle of the soil. Okay, so the task of the engineering charged with the analysis responsibility is to determine the factor safety. Generally, the factor safety is defined as tau F over tau D. Okay, so the average shear strength tau F, okay, is equal to C effective, okay, sigma effective tangent phi. Okay, so this is a more column criteria for the shear strength. Okay, and for the average shear stress that develop along the potential failure surface. Okay, so we also use the same more column criteria, okay, which is the tau d equal to CD plus sigma tangent phi d. So then the ratio between tau f and tau d, so it becomes C plus sigma tangent phi over CD plus sigma tangent phi d. Okay? So then we have FC and also Fphi, which is C over CD, tangent phi over tangent phi d. Okay. So if Fs equal to Fc and Fphi, when Fs is equal to 1, the slope is in a state of impending failure. Generally, a value of 1.5 for the failure safety with respect to the strength is acceptable for the design of the stable slope. Okay, so we need to make sure that the factor safety, okay, by using the conventional approach, the value for the factor safety is greater than 1.5. Okay, in this method of analysis, okay, we have two type of approach that usually been used. Okay? So the first one is the linear methods, and the second one is the non-linear methods. Okay? So for the linear methods, relatively simple. Okay, where for the linear method, usually we use for the infinite slope analysis. Okay, for the finite slope, okay, we also can use the linear failure plane methods. Okay, so analysis of the case of V is equal to U for the undrained conditions, and the wedge failure analysis. Okay, so while for the non-linear methods, okay, so the use of the method of slices necessary for irregular slope geometry, okay, non-uniform soil conditions, and by using this linear method, we also can include the seepage inside the soil. Okay, so that is the method of analysis that we will learn. Okay, okay, for this session, okay, we discuss on the infinite slope. Okay, uh, on how to what we call to determine the stability for the infinite slope. Okay, and how to calculate the infinite slope factor safety. Slope that extend or relatively long distance and has consistent subsurface profile can be considered as infinite slope. Okay, so I mean that as I mentioned before, the surface slope surface is relatively long, okay, compared to the height, okay, is considered as a infinite slope. Okay, so at the same time, okay, um, there are reference book also. If we only concentrated on the slope surface by ignoring the top and toe, so we also can use the same approach, okay, to analyze the stability of the slope. Okay, so failure plane parallel to the slope surface when we consider this happen. So we also can use the linear failure plane methods. Okay, we examine one layout of a infinite slope. Okay, so then we assume this is a weak soil layer. Okay, so from there, the what we call the width of this weak failure part is considered as the length of L. Okay, so then the this block width is considered as W. Okay, so definitely there will be W N, which is a normal load, normal force acting on the failure plane. Then we also a driving force of WP acting perpendicular parallel to the slope surface. Okay. So then we have what we call as a beta, which is what we call as the angle of the slope. Okay. So for the resistance, okay, force, we have here CL plus WN tangent beta. Okay. While for the driving force, okay, WP, okay, the equation is let me so the W's and R ER okay, there is a WP that uh, considered as a driving force. Okay, okay, now we look on this derivation, okay, on how to get the factor safety value, okay, based on these sections of the infinite slope. Okay, so for this case, this infinite slope, where the water level is far from the slope structure. Okay, so we consider it is a dry slope structure. Okay, so we have there beta. Okay, then this considered as the length of the slope block or the slope block. Okay, so then we have a W. So to determine the width of this block, okay, so the volume of the soil elements multiply with the weight, unit weight of soil. Okay, so unit weight of soil is gamma, and then the volume of the soil element is L times H. Okay, so force perpendicular to the plane, which is NA. Yeah. The plane is AB. This is the plane of AB. NA is equal to W cos beta. Okay. So then we use the W as gamma LH. So it becomes gamma LH cos beta. Okay. Meanwhile, for the force parallel to the plane AB, okay, which is the TA, okay, is W sine beta or gamma LH sine beta. Okay, basically this is not N, this is P. Okay. That's why I try to find the W, not WM, it is WP. Okay. Okay. So force parallel to the plane AB, which is the TA, is W sine beta. Note that this is the force that tend to cause the slip along the plane. Okay. So those the effective normal stress and the shear stress at the base of the slope element are okay. So then to make it into a force or stress, okay, to make it into a stress, this force we may divide with the area. Okay. So then gamma LH cos beta over the area of the base, this is the L, this is L. So because it has what we call, it has a sloping, so then we need to make it into yeah, if this is L, so this is the, we need to use the trigonometry equation then. So this is beta. Okay. So to get the L in this direction, so cos L over AD, okay? So this will be cos beta. Okay? So then AD, if you move to the left and cos will be on the right. So it becomes L cos beta. Okay. So from there, the stress due to the shear stress, okay, um, become gamma h cos squared beta, and the shear stress, okay, from the parallel of the on the parallel of parallel to the failure, it become gamma H cos beta sine beta. Okay. So the reaction of the W, okay, is an equal and opposite force R. The normal and tangential component of R with respect to the plane AB are N R cos beta equal to W cos beta, TRR sine beta equal to W sine beta. Okay, so there is NA here and also NR, TA and also TR. So for equilibrium, the resistive shear stress that develop at the base of the element is equal to TR over base element gamma H sine beta cos beta. So the resistive shear stress also may be written as TD CD plus sigma tangent phi D. Okay, so those TD is equal to gamma H sine beta cos beta, okay, which is equal to CD and then sigma, where we gain from here, okay, is gamma H cos square beta, okay, tangent phi. Okay, so what should we do? Okay, so then we do some rearrangement, okay, where CD over gamma H is equal to sine beta cos beta minus cos square beta tangent phi, then it become cos square beta tangent beta minus tangent phi. Okay. So based on the previous equations, okay, for the FC and FE, okay, okay, then we rearrange, okay, this equation, okay. Later on, we get the equations, okay, which is C prime over gamma H cos square beta tangent beta plus tangent phi prime over tangent beta. Okay. So this is the simplified approach, okay, where the derivations work, okay, for what we call it uh, for the slope, which is where the groundwater is far from the slope surface. Okay. So, okay, let's say if you want to determine the factor safety, okay, for the infinite slope stability for the groundwater, where the groundwater for the dry slope or for the groundwater is far from the uh, slope surface. So then you can use this, what we call as simplified equations. Okay. Later on, I will show with you how to use this equation. Okay. Okay, for granular soil, when C is equal to 0, then the factor safety become equal to, when C is equal to 0, so the factor safety become equal to tangent phi over tangent b beta. Those factor safety is depending on the height and the slope is stable as long the degree of the slope is less than the phi. Okay? So this is what has been discussed before. Okay? If the beta is less than the phi, so then we can say that the factor safety uh, is greater than 1. Okay? So if a soil possesses cohesions and frictions, the depth of the plane along which critical equilibrium occur may be determined as factor safety is equal to 1. Okay? Then at that case, the height of the slope is considered as a critical height. Okay? So let's say if we want to determine what is the critical height of the slope, okay? So we rearrange this equation, okay, where we put the factor safety on the HCR on the left and the rest on the right. Okay. From there we can get the what we call as the critical heights. Okay. So this is the example of the derivation. Okay. To get what we call as the uh, critical heights of the slope, where we assume the factor safety is equal to 1. Okay. So as we can see here, okay, the value, sorry, okay, the equation is similar. Okay. Then this equation can be used to determine the critical height for the slope where the groundwater level is far from the slope. Okay. Okay, the next example, okay, when we evaluate the stability for a slope that have a groundwater on the at the surface. Okay? So this is the example of a ground slope where the groundwater table located at the surface of the slope. Okay, slope with stability with seepage. We assume that there is a seepage through the soil and the groundwater level coincides with the ground surface. Okay, the shear strength of the soil is given by tau F equal to C plus sigma phi tangent phi. Saturated unit weight of the soil may be used, okay, because previously we used the bulk unit weight. So then for this case, we use the saturated unit weight. Okay? So those for the NR, okay, and also for the TR, so R cos beta, W cos beta is equal to gamma saturated LH cos beta. ERR sin beta W cos beta equal to gamma sat and his sine beta. So then from the force, we derive it as a stress. So then we have a normal stress and shear stress, or we call as a resistant or shear strength, okay, and also the shear stress. Okay, so NR over L over B beta is equal to gamma sat H cos square beta. TR over L over cos beta is equal to gamma sat H cos beta sine beta. Okay. So the resistive shear strength also can be given by, okay, this is for the resistive stress, okay. CD plus sigma tangent PD or equal CD plus sigma tangent nu. Nu is the pore water pressure because there is a seepage or the groundwater level on the top of the slope surface. Okay, where nu is the height of the water in piezometer, please at F. Okay, and times with the unit weight of water, so it becomes H gamma W. Okay, so for the H, okay, it becomes H cos square beta. Okay, those the new or the pore water pressure is gamma W H cos square beta. Okay, then we include this equation inside the tau B. Okay, then we obtain CD gamma H cos square beta tangent phi D. Okay. Later on, okay, we simplified the equations. Okay, uh, for the driving and also for the resisting. Okay, only for the driving because the soil, oh sorry, because the water doesn't experience a shearing, so then we may use what we call as saturated uh, unit weight. Okay, so we will not use the effective unit weight for the driving. Okay, so while this is for the strength, okay, then we have cos square beta times tangent beta minus gamma over gamma saturated tangent phi d. Okay, so then the effective unit weight is equal to saturated unit weight minus gamma w. Okay, so that is for the derivation for the what we call unit weight effective. Okay, so then rearrange, okay, to determine the factor safety. Uh, for the seepage cases, okay, the factor safety or the formula that we may use, okay, is derived as shown, sorry, as shown in this example, which is C prime over gamma saturated H cos square beta tangent beta plus gamma prime over gamma saturated times tangent phi prime over tangent beta. Okay, that is for the factor safety for this seepage type of slope. Okay. So then similar like the previous example, okay, where when the C is equal to 0, okay, usually when C is equal to 0, we deal with a sandy type of material. Okay? So then the factor safety for the sandy type of material, okay, we can use this formula to determine the factor safety. For the case where whatever is far below the failure plane, so then similar from what we have discussed before, the factor safety is equal to tangent P over tangent beta. Okay. So that is for the slope that have a groundwater level at the surface. Okay. However, in some situation, or most of the situation, the groundwater level is not at the surface. Okay? So it can be, it can be at this place, okay? Or it can be at any other place. Okay? So means that this approach or these equations only limited to the case where the groundwater level is located at the seepage. Okay, so what should we do when we deal with this kind of situation? Okay, because we could not use this uh, simplified equation since the groundwater level is at the surface, and also we cannot use this uh, approach where the groundwater level is far from the surface. Okay, so that is the limitations of any simplified equations. Although it's very simple to be used, but still have a limitations. Okay, so for me, it is better to use a fundamental approach, okay, to determine the factor safety, okay, where we need to use, sorry, where we better to use the concept of tau F over tau M. So that will be more that will be more uh, appropriate to be used, okay? Because uh, if we deal with situation where the groundwater level at a different height, so then we use the basic equation, okay, to determine the factor safety for the slope. Okay. Okay, note that when C is equal to 0, the factor safety is independent of the height of the slope. The slope will be stable as long the slope angle beta is less than the internal friction angle. If both cohesions and angle of friction angle is not 0, then the critical condition will be achieved. Okay? So for total stress analysis, the shear strength parameter C and P are used with a 0 failure of M. Okay. Okay, so in order to overcome the limitation from the previous approach, okay, so we may use this kind of approach, okay, to determine the stability for the infinite slope, where we use the concept of M, okay, to overcome the limitations from the previous equations. Okay? So how to use this M approach? Okay. So basically, this M approach, okay, is from the basic or from the fundamental equation to determine the factor safety. Okay. We not simplify the equations similar like the previous example. Okay. Um, okay. Yeah, I will share with, I will, okay, during the any test of equation, any test of final, okay. So, I will give the basic equation, okay. So then you can easily uh, use it, okay, by understand the concept of tau f over tau m. So in here we have the tau f, okay, and also the derivation of the other equation, okay. So for example, we have sigma and we also have mu, okay. Then we have a tau m there, okay. So in order to determine the factor safety, so you need to solve the tau f, but including the sigma and mu, and then you need to divide it with the tau m. Okay. So what is m? Okay. So m is the ratio, okay, between the height of the water and the total height of the slope. Okay. Is the W over H. Okay. Okay, let's say if the water level is located at the surface, okay, so the ratio between HW over H is equal to 1. Okay, so if this is equal to 1, so then we may eliminate this sub-equation. So then this will be equal to 1. So same goes with this one. So then this will become 1. So this also will become 1. Okay? So if the groundwater level is located at 2 meters below the slope surface, okay, and the thickness of the slope is 6 meters. Okay? So if this is 4, okay, so the M is 4 over 6. Okay? So then we have a combination between gamma and also gamma saturated. Okay. Okay. So for me, it's better to use the basic formula, okay, because it's more flexible and can be used to any type of situations based on the groundwater level locations. Okay. Okay, don't worry. We will go for the example after this. Okay. So I will explain in detail and then we will look on the difference. We compare with the approach from this fully saturated and dry equations. Okay. Okay, now we go for the example. So we open for the example. Okay. Okay, this is an example on the use of dm. Okay. Then we try to use the simplified methods, okay, to check for the result. Okay. So basically, this is the derivation work, okay, where we have a tau f. Okay. Then we get the tau m. Okay. So they also what we call as simplified the equation, okay, to get the similar from what we have discussed before. Okay. Okay. Okay, we look on this example on the use of the M methods. Okay. Okay, a long natural slope in the fissure over consolidated clay is inclined at 12 degrees the horizontal. The water table is roughly at the surface of the slope. Okay. A slip has developed on the plane parallel to the surface at the depth of 5 meters. The saturated unit width of the clay is 20 km per meter cube, and the peak strength parameter C are 10 and phi are 26. Okay. Determine the plate safety along the slip surface. Okay. So for the solutions, okay, for beta is equal to 12. Okay, so then we try to draw the problems. Okay. Okay. So we have a slope with an incline of 12. So the water table is roughly at the slope surface. A slip has developed on the plane of surface of depth of 5 meters. Saturated unit weight of the clay is 20. Okay. And the peak strength parameter C is 10. And the phi is equal to 26. Okay, determine the velocity along the slip plane. Okay, so then we extract the problem. Beta is 12, Z is 5 meter, okay. M is equal to 1, because M is the height of the water over the height of the slope. So since the situations where the water level at the surface, so then M is equal to 1. Okay. Saturated unit weight is 20, C is 10, P is 26. Okay. So then, okay. So this is the formula where tau M, sorry, tau F over tau M tau F over tau M to get the factor P. So for the tau M, okay, so the formula is 1 minus M saturated, unit weight, plus M saturated, unit weight saturated, times Z sine beta cos beta. Okay, so then M saturated times Z sine beta cos beta. Okay, okay, for the shearing, we may not use what we call as an effective unit weight. Okay, because I mentioned for the tau m, the saturated unit weight is used and not an effective unit weight. Okay? So it means that this saturated unit weight, you need to use, okay, not use the effective unit weights. Okay, so m times saturated unit weight times z. Z is 5 meter. Sin beta 12 cos beta. Okay. So then you obtain 20.3. Okay. So that is for the tau n. Okay. So to get the tau f, okay, we need to determine what is the sigma and also the pore water pressure. Okay. So C is given, okay, but we need to calculate first the sigma and also the pore water pressure. Okay. So for the sigma, this is the equations. Okay. 1 minus m unit weight plus m unit weight saturated times z for square beta. Okay. So from there, we get 95.5, where 1 times 20 times 5 times cos square 12. Okay. So that is for the sigma. Okay. Then for the pore water pressure, okay, m times z times unit weight of water. Okay. So in this case, we use 9.8. Okay. You can use 10 and make it is, and it's not necessary to use 9.8. Okay. So 1 times 5 times 9.8 times cos square 12. So then we obtain 46.8. Okay. So that is new. Okay. So sigma minus new tangent phi. So the tau f is equal to 33.8. Okay. So 33.8 divided with 20.3, we obtain 1.66. Okay. So this is the conventional methods. Okay. So for the any man-made slope, okay, we should make sure that it is greater than 1.5. Okay. So now let's try to use the simplified methods. Okay. Okay. This is the questions that stated slip has developed on a plane parallel to the surface at a depth of 5 meters. Okay. So in reality, okay, to use the linear failure plane, okay, we need to go to the site. If we observe there is a clear failure planes at the sites, okay, so then we need to measure. We can also use what we call as the linear failure plane methods, okay, to get the factor safety. Okay. But for this case, the question has already stated that it is 5 meter slip surface thickness. As far as I know, we need to look it at the side. The bollards we cannot estimate uh, where is the location of the slope, where is the location of the slip surface. Okay. Okay. So now we look on the simplified equation. Okay. Okay. We will go for the EC7 after this. Okay. Let me show you the conventional method first. Okay. Okay. So this is the use of the M approach. Okay. So now uh, let me, yeah, you need to look on the slide. Okay. That we use the equations, okay, for the saturated soil. Okay. So this is the formula to determine the factor safety, okay, when the groundwater level at the top or at the surface of the slope. Okay. So yeah, we try to check either we obtain 1.66 or not. Okay, the factor safety is C gamma sat H cos square beta tangent beta plus effective unit weight saturated tangent phi over tangent beta. Okay. So what is the value of C? So C is equal to 10. Saturated unit weight is equal to 20. H is 5 meter. Cos beta is 12. Okay. Tangent beta 12 plus effective, which is uh, 20 minus 9.8 over 20 times tangent phi, in this case 26 over tangent 12. Okay. So then we calculate 10 over 20 times 5 times cos 12 cos 12 tangent 12, 0.49. Okay. So then 20 minus 9.8 over 20 times tangent 26 over tangent 12. 1.17. Okay. So 0.49 plus 1.17 plus 0.449. Okay, then we also obtain 1.66. Okay. Okay. So means that with the use of the simplified equation, okay, and also the use of the m, okay, we also obtain the same result. Okay. However, okay, if the groundwater level is not at the surface, we cannot use this equation. Okay. Yeah. If we do some, if you improvise this equation, perhaps we can include the groundwater level, sorry, the difference level of groundwater level. Okay. Okay. So that is for the M approach. It's still on a conventional method. Okay. However, at least you understand, okay, if you deal with different type of uh, water level, so then you can use these methods. Okay. So that is for the conventional approach. Okay. Now we look on the use of the EC7. Eh? Mhm. All right. Okay. Okay. Hope we have a little bit background on EC7 because I will not explain in detail, okay, on the EC7, okay, by showing all the table, because in here is already mentioned the table. It's already mentioned that there is the use of table. Okay. Okay. So this is another approach similar like M, okay, where we use basic formula, okay, not a simplified formula, okay, to solve the problem for the infinite slope. Okay. So we have here a figure of, sorry, a figure of Q31. Assuming is it an infinite slope of C and phi soil, assuming the groundwater table is far below the slope surface, calculate the design shear strength and shear stress along the failure surface. Okay, so for this case, we may not determine the over design factor, okay, because in uh, Euro code 7, okay, so the last product we call as a over design factor. Okay. So this over design factor uh, is the ratio between the resistance and actions. Okay. So if the ratio between resistance and actions is greater than 1, okay, so it means that it comply with the EC7. Okay. Okay. So for the EC7, we have two combinations. Okay. For design approach 1, okay, they call as design approach 1, under the design approach 1, we have two what we call as combinations. Okay? So we have combination 1 and we have combination 2. Okay? So for design combination 1, okay, so this is the parameter or the notations or we call as a partial factor safety involved. Okay? Where we have A1, M1, and R1. So A1 is considered as an action. Okay? So in previous British standard, okay, so it has what we call as a dead load and live load. Okay, so for under the EC7, okay, it also have similar like the previous one or like the British standard. Okay, it also have they call as a permanent, which is dead load, and variable, which is live loads. Okay, so that is for the actions. Okay? So under the actions, okay, they have what we call as a favorable and unfavorable. Okay, so favorable means that any type of action, okay, can provide a stability for the geotechnical structure. Okay, if unfavorable, okay, it contribute to the instability of any geotechnical structure. Okay, for example, for slope, resistance can provide instability while driving provide to the resistance can provide for stability, driving will provide for the instability. Okay, that is for the A1. Okay, means that for the stability, we consider as favorable, while for instability of the actions toward any geotechnical structure is considered as unfavorable. Okay, we have M, material. Okay, so under combination 1 and combination 2, slightly different in terms of number. Okay, then we have also R, which is resistance. Okay, so for driving, there is no resistance, so no need to apply the resistance, partial factor safety. Okay, for M and R, okay, we need to divide it, while for actions, we need to multiply the value or the characteristic value. Okay, okay, for example, for this case, 18, 20, 15 is considered as characteristic. Okay? When we apply the partial factor safety, we call as a design parameter. Okay? Okay. So we look on the example, this example. That is very brief. Okay? If you want to know in detail, so then I'm not sure at which subject we discuss. On the advanced foundation. Advanced foundation, I explain in detail, okay, on the EC7s. Okay? Okay, for combination one, under the actions, okay, so this is considered as permanent unfavorable. While this is permanent favorable, okay, because in slope we have driving and also resistance. So resisting is considered as favorable, driving is considered as unfavorable. Okay. So then for the material, okay, we have gamma T, gamma C, and gamma gamma. Okay. So for material, we divide it with the partial factor safety. While for the resistance, also we divide it with the partial factor safety. However, for the action, we multiply it. Okay. Okay. Only for the phi or internal friction angle, okay, we need to use the tangent methods. Okay. So for the tangent methods, okay, to get the design's parameter, okay, the material value, we tangent it and divide with the gamma phi, then inverse tangent it because the original equation, this is the tangent. This also have a tangent. Okay. So to get the phi d, so move this to the left and right. So then we use the inverse tangent approach. Okay. So then the phi d is equal to 15. Okay. For combination one, okay, there are no significant difference. Okay. Because all the value of the M1 is equal to 1. But when we go for the combination 2, okay, phi gamma phi have a difference. It's not 1. Okay. So later on we can see if we not using the tangent approach, definitely we will have the difference, or we do a mistake to get the or to solve the problems. Okay. So that is for the phi d. Okay. Then we go for CD. Okay. Then gamma D. Okay. So the shear strength can be determined using equation K. Using this equation for the shear strength. Okay. As I mentioned, this is a similar like M, but we not use the term of M. Okay. So that is the equations for shear strength. Okay. So since shear strength contribute to the stability, okay, so the stress from the normal stress, okay, we multiply with the partial factor safety favorable, permanent favorable. Okay. So CD is obtained from the coefficients, okay, gamma, sigma, because sigma is the force, okay, or actions. So then we multiply the action with partial factor safety. For this case, it is favorable, okay, times with the unit weight times with the height. Okay. Then at the same time, the full equation is cos square I. Okay, so that is for the sigma times with the tangent phi d. So the S value is equal to 43.39. Okay. So then this S value, we divide it with the gamma RE to get the shear strength or to get the design shear strength. Okay. So when we divide with the R, gamma RE, okay, so then we obtain the same with the characteristic of S. Okay. We still need to show this procedure, okay, because if we do not divide it with the partial safety, we not get the designs parameter. Okay. So that is for the S. Now we go for the driving value or driving stress. Okay. So since this driving stress contribute to the instability, okay, so then we implement the gamma G gamma D, okay, which is the unfavorable partial factor safety. So 1.35 times 18 times 5 times sine 10 times cos 10, we obtain 20.78 for the tau D. Okay. So basically, if we want to count for the over design factor, this 43 over tau D, which is 20.78, is the over design factor 43.39 over 20.48. So we obtain 2.11. Okay. So 2.11 basically is greater than 1. So then it complies with the EC7's methods. Okay. So that is for the first combination 1. Okay. So, okay, then I go for the combination 2. Okay. Where we have K2 plus M2 plus R1. Okay. So for the combination 2, okay, is one to look on the effect of the material, while combination 1 is one to look on the effect of the actions. Okay. So then we try to solve the question based on combination 2. Okay. Okay, this is what as I mentioned. Under the combination 2, we have a little bit large partial factor safety, okay, which is 1.35. Okay. Okay, you look on the difference happen if we divide 15 with 1.35. 16 over 1.35. So then we obtain 11.11. Okay. Although the value is not too huge, okay, 11.23 compared to 11.11. Okay. However, when we want to use it for the design of the shallow foundation, okay, there will be a domino effect happens. Okay. For example, to get the phi D, okay, we need to use the tangent. Okay. If we not use the tangent, so then although it has a difference of, for example, 11 to 3 and 11 of 11, then for the foundation design, especially for the shallow foundation, okay, we need to get the NC, NQ, and N gamma. Okay. So there will be another second error happen because we may use a different value of NC, NQ, and gamma. Okay. Then the third error when we calculate for the Q ultimate. Okay. Although at the first place it only have a very small difference, but when we use it in design for the foundation, so we will get multiple error, okay, doing our calculations. So that is for the what we call as for the phi. Okay, then we calculate for the C, gamma, okay. Then the shear strength determined as 32.14, okay. And SD after divide with the partial capacity of resistance, 32.14 also, okay. So for the tau D, the shear stress, okay, this contribute to destabilizing. Okay, then we use the uh, unfavorable partial capacity. Then we obtain tau D is equal to 15.39. Okay, so to get the overall design factor, 32.14 over 15.39. Okay, so then the partial capacity is equal to 2.1. Okay, so both of the combinations comply with the EC7. Okay, so by using the EC7, we need to make sure that both of the calculations is comply, okay, with the EC7. Okay, let's say if one has not been complied, so then we cannot proceed to use the result. Okay, so then we need to do some uh, adjustments, okay, on the either on the geotechnical structure, okay, or the loads that apply on the foundations or on the geotechnical structure. Okay, so that is for the first example. Okay, now we go for the second example. Okay, so perhaps this will be the last example for today. Okay. Okay, so hopefully you understand it on the use of the EC7. Okay, then I also will repeat again based on this example. Okay. So consider an infinite slope of C and phi as shown in figure Q32. Determine the overall design factor against sliding. Okay, for this case, we calculate for the overall design factor. Assuming the interface friction angle between the sliding and stationary slope surface, stationary subsoil is 20. Okay, so that means that the phi is 20. The critical height of the slope, the overall design factor against sliding, if the ground table is located at 2 meters below the ground surface and seepage occurs, use the saturated unit weight of 19 and assume other parameter unchanged. Okay, so we have 3 questions there. Okay, the first one, okay, the overall design factor against sliding. Second, the critical height. And third, okay, is the groundwater table at 2 meters below the ground surface. Okay. Okay. So for the first one, determine the overall design factor. Okay. So we use the combination one. Okay. Gamma G 1.35, gamma G favorable. This is unfavorable. This is favorable. gamma phi, gamma c, gamma gamma, and gamma r. Okay. So start first with the M1, okay, CD, gamma D. Okay. So then the design shear strength and shear stress along the failure plane must be considered to determine the overall design factor of the slope. Okay. Okay, we have delta T. This is favorable times 17 times 6 cos square 25 tangent 20 and then divide with the resistance. Okay. Then unfavorable times 17 times 6 times sine 25 times cos 35. We calculate as 1.15. Okay. So although the value is less than 1.5, but based on the EC7 approach, okay, so over design factor is greater than 1 is okay. Okay. So then we look on the combination 2. We have A2, M2, and R1. Okay. So for the gamma G, gamma favorable, okay, gamma phi, gamma C, gamma gamma, and gamma RE. Okay. So first for the saw properties M1, sorry, M2, phi D, CD, gamma D. Okay. Then determine the shear strength and shear stress along the failure plane, which is the over design factor. Okay. So for the over design factor, 22.22 plus 1 times 17 times cos square 25 tangent 15 divide with the resistance over gamma G gamma favorable unfavorable is sine I cos I. Okay. So we also obtain 1.15 similar with the combination 1. Okay. Both combination 1 and combination 2 actually yield similar, okay, which is 1.15. Okay. So now we look on the combination 2, sorry, combination 1 for the question B. Okay. So for the question B, determine the critical height of the slope. Okay. So what is the critical height of the slope? Okay. Critical height of cohesive soil can be determined by taking the overall design factor to unity, which is the overall design factor is equal to 1. Okay. Then we have combination 1, A1 plus N1 plus R1. Okay. 1.35 for the gamma G favorable. Okay, then we have gamma phi, gamma C, gamma. Okay. Then gamma RE, which is equal to 1. Okay. Then design soil properties, gamma D, FID, CD, gamma D. Okay. Then with the use of the equations between S and tau, okay, so we rearrange it and put S on the left, tau on the right, okay. So then try to include all the important parameters to determine the S and to determine the tau. Okay. So from there, we can rearrange where we put H on the left and the rest on the right. Okay? It is similar with what we have seen in the slide, okay, to determine the H critical. Okay? So then CD over gamma D cos I gamma G gamma R sin I gamma G favorable cos I tangent phi, okay, we obtain H is equal to 8.09. Okay, so that is for the combination one. Okay, then we go for combination two. Okay, gamma G favorable gamma phi gamma C gamma RE. Okay, so then get this phi D CD delta A sigma the gamma D. Okay, so using the equations for over design factor equal to 1, so then we obtain these equations, rearrange, okay, and put it on the left for the H, the rest on the right. Okay, then we also obtain 8.09. Okay, so combination 1, combination 2 yields similar critical heights, which is 8.09. Okay, so that is for the question B. Okay, so now we go for the last example on the question C. Okay. Okay, I will mention which combination that you need to use. Okay, okay, either you may solve it based on combination 1 or you may solve it based on combination 2. Okay, so now we look on the C. Okay, so for the C, the groundwater level is at 2 meter below the slope surface. Okay, then we have saturated unit weight of 19. Okay, okay. Note that this problem involves combination of soil above and below groundwater table. Hence, the appropriate unit weight of soil and strength parameter must be selected and applied judiciously. Okay, so we have combination 1. Okay, gamma G, gamma favorable, gamma phi, gamma C, gamma. Oh, I guess this is wrong. Eh? This is combination 2. Okay, this is 1. Okay. Okay, so then phi D, phi C, phi D, CD, gamma D. Okay, okay, okay. There are some error here. Okay. I will let you know what is the error. Okay. Okay. So, okay, for this example, okay, combination 1 supposed to be 1 for gamma phi and also gamma C1. Okay. So this is correct. Phi D, CD, and gamma D. So that is correct. Okay. So this is 1.35 for the M2. Okay. Okay. Okay, this also correct. Okay. Um, as I mentioned before, for the driving force, okay, or they call it a design destabilization stress. Okay. Uh, the tau D, okay, the unit weights of water, we may not use the effective unit weights. Okay. We use the what we call as the saturated unit weights. Okay. Since water cannot resist shear stress, so then we use the saturated unit weight for the destabilizing. Okay. So design resistance stress over design destabilizing stress. Okay. Okay. For the 5D, okay, this is not 2.22. Sorry, for the CD, it's not 22.22. Okay. So the CD is 30. Eh? Okay. Unless if we are referring to M2. Okay. So this is 30. Okay. Plus 1. Okay. Multiply 17 times 2 plus 19 minus 10 times 4. Okay. Cos 25 and tangent 20. Eh? This is tangent 20. Okay. Tangent 15.09 is from the combination 2. Okay. So then what we gain is not 0.66. Eh? Okay. So then we need to calculate again. So what is the new value for the over design factor for this example? Okay. Okay. 30 plus 1, okay, times 17 times 2 plus 9 times 4, okay, cos 25, cos 25, tangent 20. Okay. So the value is 50.92. Okay. Then for this, the design destabilizing stress, okay, 1.35 times 17 times 2 plus 19 times 4 sine 25 cos 25. So then we obtain 56.88. Okay. So then 50.92 divided with 56.88. So we obtain 0.89. Okay. For the first combinations. Okay. Then we try to solve for combination 2. Okay. So the CD is equal to 22.22, okay, plus, okay, 17 times 2 17 times 2 plus 9 times 4 cos 25 cos 25 tangent 15.09. Okay. So plus 22.22. Okay. We obtain 37.72. Okay. Divide 15.15. Okay. So divide with, this will become 0. It's at 1. Okay. 17 times 2 plus 19 times 4 times sine 25 cos 25. So then 42.13. Okay. 42.13. Okay. So then 37.72 divide with 42.13, we obtain 0.89 as well. Okay. So 0.89. Okay, for the second combinations. Okay. So then we compare with the example number 1. Okay. When the groundwater level is far, the the overall design factor is more than 1. Okay, so it means that it is stable. When the groundwater level at 2 meters below the ground surface, the overall design factor has become 0.89. Okay, so it is less than 1. Okay, so it means that with the increment of groundwater level, so it may contribute to the instability of the slope. Okay. So that is for the what we call for the infinite slope. Okay. I guess as I told you in the early stage, we discussed on the introductions and also on the infinite slope with the example. Okay. So tomorrow, I will touch on the finite slope. Okay, with the example. Okay, and I will add another notes. Okay, at least we have covered 4 uh, topics. Okay, for today and tomorrow. Okay, so with that, I end my today class. Okay, we will meet tomorrow at 7 a.m. because as I mentioned earlier, I need to go to KL by 9:30. Then we will continue at 2 and then try to complete by 4. Okay. Okay, that's all for today. Same link, yeah. That is my personal link. Okay, the webback link. Okay. So see you tomorrow. Okay, Assalamualaikum and good evening. Okay, you're welcome.